Hi, Zach. Welcome to lesson 113. And today's lesson is actually really cool because we're going to learn about direct variation and also inverse variation. And this is actually really, really useful for real life. I know a lot of times we're like, I don't know how you'll actually use this in real life, except for they love this stuff on AP tests. But this is actually super useful in real life. I actually use it all the time, and I'll show you ways that I do that, okay? So here we go. First of all, let's start with a joke like usual. Why was 5 afraid of 7? Because 6, 7, 8. That's a good one, right? Your face is probably looking like Luke right now. Okay, here we go. Direct variation. We're going to start with the direct and then we'll talk about indirect. Okay, so what direct variation means is that you are starting out with two variables, two things that change. And in this first example, they talk about the number of boys, which they designate as B, and the number of girls, which they designate as G. And if they are directly related or they have a direct variation with each other, that means that if the number of boys goes up, then that means the number of girls goes up. And if the number of boys goes down, the number of girls goes, I was going to do a G, that also goes down. So that's what it means by direct variation. And you'll notice we can write an equation for direct variation like this. And this is actually a specific way that the ratios go up because they have a coefficient right here. And this particular coefficient is, well, I'll show you what it means because it actually has a specific name. And what it means in this situation, and it can vary, is that these are your two unknowns, the number of boys and the number of girls. And if you have, if you have one girl, let's put in the number 1 for here, then the number of boys is going to be 2 because it's 2 times 1. And so there's twice as many boys as there are girls. So that's important for you to know because if you have an equation like this, an easy way for people to mess you up on it is they're going to say, which is more, the number of boys or the number of girls? And you would think because the number 2 is over here by the girl side that the number of girls is higher, but it's not. And just think about it this way. Put in a number 1 for the number of girls. That means there's only one girl. How many boys will there be? There will be 2 because it's 2 times 1. So you know there's more boys than there are girls, and turns out there's twice as many boys because if you put the number of girls as 2, plug that in right there, 2 times 2 is 4, so the number of boys is going to be 4. So this is a direct variation. As the number of girls goes up, so you can put 1, 2, 3, 4, 5, anything in that number, like the number 10, the number of boys goes up, and it goes up directly with the number of girls. So these are keywords. Directly, I'll show you all of the keywords in a second, but directly, direct variation, proportional to, things like that. Now, the way that these two numbers are related is designated by this. It doesn't have to be a 2. It's just some sort of constant. And it has different names, but it's a constant of proportion or a constant of proportionality. Okay? And these are your two unknowns, the boys and the girls. All right. Now, if there's another classroom, there might be 3 times as many boys as there are girls. See, you would probably not like that situation because there's not enough girls to go around with all the boys if they pair up. So again, in this situation, it's even worse for the boy than just twice as many girls because there's 3 times as many boys as there are girls. So if there's 10 girls, let's put in the number 10 here, the number of boys is going to be 30. That's a lot, okay? So be sure you can answer this question. Are there more boys or girls? And the relationship between the number of boys and the number of girls is designated by K, which is the constant. So these are the key words for you to know that there's a direct variation. It's either going to say direct variation, it's going to say direct proportion, or a constant of proportionality, something like that. They're directly related, okay? It varies directly. All of those are key words. Wait a second. Okay, so you have to know that constant, K, of proportionality. So when you solve any of these problems, you need to know the constant of proportionality. Now, they might tell it to you. They might say there's twice as many boys as there are girls, or they might say K is equal to 2 or something. But they might also say if the relationship between boys and girls is consistent, and in one class there's 10 girls and 20 boys, what is that constant of proportionality? And then you will have to figure it out. So before you can solve any of these problems, you have to know the constant of proportionality. So the first thing you do is solve for K. This will make sense when we start doing some examples, I promise. So absolutely, you have to do that first. So they could tell you the number of boys and the number of girls. This is very useful in lots and lots of different scientific applications. Even Charles Darwin thinks so. Oh, I meant to circle him, but that's okay. All right, so they might say, here's another example, the number of boys is 6 times as big as the number of girls, okay? But if they don't tell you that K, so in this example on page 474, like 3/4 of the way down the side, that page, they say, if we're told that the number of boys and girls in any room of the school, you can figure out K. So they say the number of boys is 30. The number of girls is 5. What's the constant of proportionality? And if they tell you that it's directly related or it's the same in every classroom, we know that there's more boys than girls, so boys is going to be equal to K times G, and then you plug in those numbers. 30 is equal to K times 5, and 5 is 6, and so that's why 6 is written here. Okay, so step 1, solve for K. Here are some equations that are used in science, like seriously, they are used. They might tell you that the weight of a substance, okay, varies directly, so those are the key words, varies directly, that's where you put your equal sign, varies directly as the volume of the substance. So the weight varies directly as the volume. So let's say it this way. If volume goes up, the weight goes up. If volume goes down, the weight goes down. And you're going to have to solve for K because they didn't tell it to us in that example. But here's another example that we use in science all the time. Force. The force varies directly, so it varies directly as the current. And here C is the current. Okay? So force varies directly with the current. All right. And that's how you would write that equation. So again, if current goes up, force goes up. I actually think of varies directly or a direct variation as the rule of thumbs. You're kind of giving 2 thumbs up. If one of them goes up, the other one goes up. Or you could give 2 thumbs down. If one of them goes down, the other one goes down. But your thumbs are in the same direction when it varies directly, every time it varies directly. Here's another one where it varies directly. The distance is equal to, or the distance traveled varies directly as the time. So distance equals a constant times time. Okay? So you're going to have to look for these key words whenever they say it. Then you know that it's the rule of thumbs. If one thumb goes up, the other one goes up. Okay? And whenever you see directly proportional, then you'll know it's an equation like this. In this example, the circumference of a circle is directly proportional to the length of the radius. So there's some constant that you can multiply times the radius to get the circumference. Okay? So if the radius goes up, the circumference goes up. That makes sense. Rule of thumbs. If the radius goes down, the circumference goes down. One more. I know you're like, okay, Mom, I get this, but this really has to stick in your head because in a little while they're going to make it very confusing. And I messed it up, and this is actually my second take doing this lesson. So yeah, good luck. Okay, this is volume. The volume of a right circular cylinder of a fixed radius is directly proportional to its height. You know, it doesn't have to be, I mean, this is an equal sign. When I think of proportional, it's actually a sign that looks like this. But they changed it to an equal sign because you have this constant. But you could also say something like this: volume is proportional to the height. And that's how I kind of think of it, because as the height goes up, volume goes up. And this sign means it's proportional. It has a direct relationship to it. Okay? Let's do example 113.1. We'll jump right in, okay? It says, the mass of a substance varies directly as the volume of the substance. As the volume of the substance. I didn't write the whole thing, but then it says, if the mass of 2 liters, so I'm going to put mass of 2 liters, if the mass of 2 liters of the substance is 10 kilograms, oh, so that's actually the mass, because mass is in units of kilograms. So I'm going to make this is the mass. That's the unit of, it doesn't make sense if I put it like that, does it? Okay, let me just erase it. I'll put, this is volume, this is mass. Because mass is expressed in kilograms, those are units of mass. Liters is expressed in volume, like a 2 liter of Coke, that would be a volume, right? So if the mass of 2 liters is 10 kilograms, what's the volume of 35 kilograms? So now they're saying, what's going to be the volume if the mass is 35 kilos? Okay, step 1. What's the step we always do first? We recognize that this is a varies directly problem, or it's proportional to. So let's read the problem carefully to get the right equation, because if you do it wrong, you'll get the whole thing wrong. It says in the first sentence, the mass of a substance, so let's write that, the mass of a substance varies directly, that's where I'm going to put my equal sign, varies directly as the volume. So mass goes up, volume goes up, but we need a constant of proportionality, okay? So the first time I did this problem, I did it wrong because I had written volume first over here because it gave us that information first in the problem, and I wrote volume equals K times M. That is wrong because when you read the first sentence carefully, you can see that it says the mass of a substance, mass, varies directly, that's where your equal sign goes, as the volume of the substance. So the constant goes with volume. So that's going to be important, and if you don't get this first step right, you will get the whole thing wrong, okay? Because that's why I had to do take number 2 on this whole problem. Now, we're going to take 2 liters, which is here, and we're going to stick it in volume. So I'm going to erase this, and I'm going to put a 2 here. Oops, let me get a different color so it's clear what I'm doing. I'm going to put a 2 there. And if you do units on it, then that might be helpful too. We'll see. Okay, and then for the mass, we're going to put in 10 kilos. 10 kilograms. So the constant of proportionality is going to be 10 divided by 2 liters. So that constant actually has units. And the constant is equal to 10 divided by 2, 5 kilograms per liter. So this will help you because if you get the units right, That'll help you. Like they might give you the wrong units for the next part of the question, but you have to be consistent with your units or you're going to have to do a conversion, right? Okay, so I'm going to erase this now because that information was only given to us so that we could find out the constant. Now that we know the constant, they want to know what volume are we going to have if we have 35 kilos. Okay, so you can take that original question or the original equation, mass is equal to K times V. And now we can take this, plug it in for K, and plug this in for, no, they want to know the volume. So plug this in for mass. Okay, so let's do that. We'll do 35 kilos, I'm just substituting now, is equal to 5 kilos per liter times how many liters? And I'll put, I don't know, X liters. You don't have to do X, you could do V. V would make more sense, huh? Okay, now we divide both sides by 5 kilos per liter. And notice when you do that, it goes to this, 5 kilos per liter. The liter goes on top because it's a fraction over a fraction. And now this is so cool. This is so cool. The kilos cancel out. This whole thing cancels out. And you're left with 35 divided by 5. And so it's 7. And you are left with the correct units too. So it's 7 liters. Sorry, I'm writing it in a highlighter, but that is the final answer. So you can see that how they did that in the book on page 475. Let's do a few more examples because you got to see it a few times for it to make sense and sink in. Let's do 113.2. The distance traversed by a car traveling at a constant speed, I didn't write the whole question because it's long, is directly proportional, remember that's the little symbol for proportional, is directly proportional to the time spent traveling. Okay, so it's saying distance, if I write that in shorthand, distance is directly proportional, that's one of the keys, step 1, to the time. Okay, so let's turn that into an equation. Okay, so let's do distance. I could do this, distance is proportional to time, or I could distance is directly proportional to a constant times time. Either one of those means that if time goes up, distance goes up. That makes sense. If the car goes, now they're giving you some information so you can figure out this constant. It goes 75 kilometers in 5 hours. So the distance is going to be 75 kilometers. Let's write that under this distance. So this is my equation. Okay, distance is 75 kilometers equals K, this is what I'm trying to figure out, times the time, which is 7 hours. I divide both sides by 7 hours. That cancels out 7 hours. K is going to be equal to 75 divided by 5, which is 15 kilometers per hour. See, you even have the units. That is so cool. Now, for step 3, we take this K and plug it in here with the new information that it gives us. How far will it go in 7 hours? So it wants to know the distance here. So let me erase some of this. The distance is going to be my new K, which is 15 kilometers per hour, times the time, which they give us, is 7 hours, times 7 hours. Look at this, hours cancels out. And the distance is 7 times 15, 15 times 7, which is 105, and the units are kilometers. I'm running out of room, but it's kilometers. Okay, cool, so this is the answer right there. And it's in the right units because you did it right. Sweet. All right, now you're getting it, right? And you're like, come on, give me another one. I can do this now. All right, let's do this one. It says, this is on the bottom of 475. Under certain conditions, the pressure of a gas varies directly. I just put proportional, but you're looking for those key words. Varies directly as the temperature. Okay, so I'm going to write that equation. It's going to be pressure is proportional to temperature. Pressure is proportional to temperature. Or I could say pressure is equal to some constant times the temperature. It's the same thing. Temperature goes up, pressure goes up. Got it. Okay, now they're going to give us information in this first part so we can figure out K. When P is 800 pascals, don't worry too much about the unit. That is a unit of pressure, but you can just write 800 P, okay? The temperature is 400 K. Again, this is another weird unit. It's a unit of Kelvin, and we use that in physics a lot of times, but it doesn't matter because we're using this information to solve for K, okay? And then the temperature is going to be 400 Kelvin, okay. Oh, that's confusing, isn't it? Well, just it's different colors. So, all right, so we're going to divide 400 Kelvin, that's units, not that constant. Divide this by 400 Kelvin. And then we see that this cancels out. K is equal to 800 over 400, which is 2 pascals per units of Kelvin. Okay, so now we plug this information, this new information of K, into that original equation. So we're going to change this to 2. I'm going to put the number 2 there. 2, and you could write the units. That's what I've been doing, but I forgot them now, so it's okay if you don't. And then it wants to know what is the temperature when the pressure is 400 pascals. So it's going to be 400 equals 2 times T. So what's the temperature going to be? T is going to be 200 Kelvin. That is a unit of temperature. Okay, cool. Now let's go over inverse variation. Inverse variation. This is different. This is not giving 2 thumbs up. This is giving 1 thumbs up, 1 thumbs down. If one goes up, the other one goes down. If one goes down, the other one goes up. And this relationship is called inverse variation. Inverse variation. So whenever you see these words, I know words, I have the best words, varies inversely or inversely proportional, then you know that this is only giving 1 thumb up. It's like the inverse universe, okay? 1 thumb up, 1 thumb up, okay? 1 thumb up, 1 thumb down. You know, I don't know. Okay, 1 thumb up, 1 thumb down. All right, so the way you express that mathematically, Shadow, get out of there. Hey, get out of there, Shadow. No. The way you express that mathematically is like this. This is the constant. And you'll notice that one of these, like volume, in this example, you have volume and, I don't know, what's the other one? Weight? V and W, whatever, are the 2 variables. This is a variable, this is a variable. One is in the numerator because you could say this is V over 1, okay? One's in the numerator, one's in the denominator. And that means if one goes up, the other one goes down. So whenever you're looking at an equation that looks like this, you know that it varies inversely. If they tell you the words varies inversely or inversely proportional, then you have to write an equation that looks like this. One's on the numerator, one's on the denominator. It makes sense because one's going to go up, the other one's going to go down. Okay, so let's summarize. With direct variation, it's an equation that looks like this. Both variables are in the numerator. So if W goes up, V goes up. If W goes down, V goes down. With inverse variation, okay, inverse variation now, the equation is going to look like this. One is in the numerator, the other is in the denominator. I promise this is super useful for real life. I promise. So you definitely have to know this. They both have two variables, both of these equations, v and w here, v and w here. But this one's directly related, this one's inversely related. Okay. They also both have a constant of proportionality. Okay. Here are some examples in science of things that vary inversely. The pressure of a perfect gas varies inversely as the volume. So pressure and volume are like this, varies inversely are the key words. So if volume goes up, that means pressure is going to go down. If volume goes down, think about what happens when you reduce the denominator. That means this number is going to go up. Okay, here's another one. The current varies inversely as the resistance. If the resistance goes up, current goes down. If the resistance goes down, current goes up. Inversely related. One's on the numerator, one's on the denominator. The velocity is inversely proportional. Those are the key words that we're looking for here. Inversely proportional to time. Inversely proportional, I'll just say that. So if time goes up, volume goes down. If time goes down, volume goes up. All right, you get it. Let's do an example. Example 113.4. Under certain conditions, now I didn't write the whole word problem because it's long. Under certain conditions, the pressure of a perfect gas varies inversely. Here's the key words that you're looking for. Varies inversely as the volume. So pressure and volume are two variables and it varies inversely. So let's start the same way we did before. Let's write an equation. The pressure of a gas varies inversely as the volume. Here's the equation we write. Okay. Step 2, they're going to give us some information so we can figure out K. When the pressure is 7 pascals, so now I'm going to take this, I'm going to plug in 7. When the pressure is 7, the volume is 75 liters. So I'm going to erase this and I'm going to put in 75. Okay, so that means K is going to be equal to 70. Let's multiply both sides by 75 over 1. Multiply this by 75. Okay, so K is equal to 75 times 7, which is 525. And then you've figured out K. Okay, now it's going to ask, what is the volume when the pressure increases to 15 pascals? So use the same equation that you just wrote. Pressure equals K over V. Now they want to know if the pressure is 15 and you know that K is 525, what is V? So it's going to be multiply both sides by V. By V, that cancels out, so 15V equals 525. Now divide both sides by 15, that cancels out. V is equal to 525 divided by 15, which is 35 liters. You can keep track of your units again, and maybe I'll do that on the next one, which is also the last one, so hang in there, okay? And using the units might help you make sure that you get the problems right, okay? One more, another. Ready? Example 113.5. This one says, to travel a fixed distance, the rate, so here's one of the variables, is inversely proportional, there's your key words, to time. So I'm going to underline, rate is inversely proportional to time. So let's write that equation. Rate is inversely proportional, so it's going to be K over time. When I think of using that proportion symbol for this type of question, I can say Rate is proportional to 1 over time. That's how I hear it in my head, and that's what we use in physics a lot of times, is sort of that shorthand. But this is the more proper way that they're teaching you how to do it, okay? So rate is equal to K over T. Now they're going to give you some information to figure out what K is, okay? So when the rate is 60 kilometers per hour, so I'm going to put rate is 60 kilometers per hour. Time is 4 hours. So time is 4 hours. You can see how they might mess you up there. Instead of 4 hours, what if they gave you the number of minutes? Then you would have to do a conversion and make sure that your units are consistent. Okay, so here we're solving for K. So K is going to be equal to 60 kilometers per hour times 4 hours, okay? I like to do it like this. That way I see it easily. The hours cancel. The kilometers stay put, so that's going to be your unit, and it's going to be 60 times 4, which is equal to 240. Is that the correct units? Yeah, I think so. Okay. Now, we're going to write that original equation again, okay, because then they're going to give us the next bit of information. The original equation was rate is inversely proportional, so it's K over T. Now we know that K is 240 kilometers. So let's write that in there. Let's do that. 240 kilometers. Okay, so that's our equation. That's the constant. Now, what they want to know is, what's the time, so we're going to be solving for time, if the rate goes up to 80 kilometers an hour? So the rate is going to be 80 kilometers per hour. Okay, so for me, it's helpful to bring T to the other side in that situation. So let's do that. So T times 80 kilometers per hour is equal to 240 kilometers. So let's divide this by 80 kilometers per hour. Because it's a fraction over a fraction, I do this. I do 80 kilometers per hour. The hour goes on the denominator now because it's a fraction over a fraction, right? So this now goes to the top. Okay, so I can see if I erase this now, and T is equal to that. Okay. Let me just fix that. Sorry, a little OCD showing. That when I do my units, it's going to be 240 divided by 80, but the units are just hours, which makes sense because they're asking for time. So time is equal to 24 divided by 8, which is 3 hours. Cool, huh? And guess what? That is the last one. You're finally done with me. Done, at least for this lesson. All right, love you, Zach. Sorry it was so long. Bye.